So our last measure of spread is the standard deviation. Standard deviation measures how much, on average, the values in our data set deviate from the average or the mean. So standard deviation, like the mean, has two different distinct variables we use to denote it. So one is S. This is our sample standard deviation. The other is sigma, our population standard deviation. So this is why we did that, words are escaping me right now. This is why we did the mean formula with the summation notation earlier, was that this would look familiar, or at least not so scary. So what we're doing here is we're taking a big old square root, and what's happening inside the square root is we are summing every observation. We're going to subtract off the mean. We're going to square that. So we're getting our deviations. We're going to square them, and then we're going to divide by n minus 1. Notice that the formula is slightly different for the population standard deviation. We're still going to take all the observations and divide by our mean, this time by the true mean, and sum them all up, square, but we are going to divide by n instead of n minus 1. So this is a big difference. Our standard deviation for the population is always going to be smaller than our standard deviation for the sample because we're going to divide by a bigger number, right? We're not doing that minus 1 piece. And this is all because in the sample standard deviation, we are using this sample mean as part of it. So there's like this kind of bit of unknown, this degree of freedom that's missing. Our computation by hand is horrible. We're going to do one silly example and then realize that we would never want to do this for a full data set by hand, which is why we are very thankful we have the calculator. So this first exercise, we're looking at Rate My Professor reviews for 3 Defense Against the Dark Arts professors. Turns out they all have an average rating of 3 and only 5 reviews. So we can't just glance at, who's better. And unfortunately, let's pretend nobody has written anything down. So we have no other information other than 5 people have averaged them out to give them a rating of 3. We can't see their scores though. For Lupin, every single student gave him a 3. For Moody, we have 2 2s, 2 3s, and a 5. And Snape, he's got basically 1 of every score, right? The Gryffindors are rating him low, while the Slytherin students are rating him high. So first thing we need to do is figure out how much did the actual observations deviate from the mean, right? Let's do our xi's minus our x bar. So every single one of these, we've been told the average rating x bar, is equal to 3. And I have calculated them. They are all equal to 3, I promise. So for Lupin, that means there is 0 deviation on every single one of those observations. And if we take 0 and square it, it's still just 0, right? Now that's just part of our formula. Right now, in terms of our formula, I'm going to go ahead and rewrite it here so we have it close. Our formula that we're using, summation xi minus x bar squared all over n minus 1. All we've accomplished is to figure out all of these. The next piece is to handle the sum, right? So we're going to do that below. We're going to say, okay, the sum of all of these is equal to 0. And now we can figure out our standard deviation. It's the square root of that sum divided by n minus 1, which is 0 divided by, we have 5 reviews, that's our n. What the hell just happened? God, that's horrifying. Whoa. Our n is equal to, I don't even know how to fix this. There we go. N is equal to 5. So this would be 5 minus 1. And 0 divided by anything is 0. Square root of 0 is still 0. So this is just 0. There is no deviation from the mean. Everything is the same as the mean. So that one's a little bit silly. But we can move on to Moody. Now for Moody, there is some deviation. This guy is 1 below the mean, 1 below the mean, the same, and 2 above the mean. So these deviations will always sum up to 0. That's just a trick about the mean. Now we need to square those because we need to say, I don't care if you're above or below. I just want to know how far everything is away from that mean. So -1 squared is 1, 0 squared is 0, and 2 squared is 4. And then again, remember our formula. We just finished finding all of these. We need to do the summation. So if we sum those up, we get that there is 6 there. Our formula tells us to take that sum, divide it by n minus 1. Why did I put 4 there? I was like, there's something wrong. I know something is wrong, but I can't figure out what it is. Divided by our n minus 1. So we get 6 over 4, which is approximately 1.2247 after you take the square root. I said which is approximately twice because I ran to go get my calculator after pausing the video. And then the last one, Professor Snape, if you feel like you want to try this out on your own, feel free to pause and do it. But again, this is not something I'm going to have you do. You could also just try typing it in your calculator and doing what we did in class to calculate the standard deviation and then checking that it's the same as what I get by hand. So here are deviations. We can square them. We can sum them. And then we can go ahead and take all of those sum deviations, divide them by our n minus 1, type that in a calculator, and find that our standard deviation here is 1.5811. So we can kind of see as you move forward, as you move across here from left to right, we're going from something that is no spread at all to a little more spread out to very spread out. And you can see the same thing happening in our measures of spread using the standard deviation. So the standard deviation has a bunch of very cool properties that are, of course, the most important takeaway. That's sort of why I take the time to calculate it by hand so we can see why those things might be issues. First, this is very sensitive to outliers or skew. If our mean is off because we have an outlier or skew, everything is going to be further away from the mean. What happens when you have mean or outlier is that it's just going to blow up when you have a outliers or a skew. It's not like the mean where it's going to get pulled towards wherever that skew is. Even if we had a bunch of low outliers, that's just going to pull up our standard deviation because it means that we have more spread when we take everything into account. It's still our best measure of spread if we have something that is symmetric, unimodal, nice, pretty data. In fact, if it is nice and unimodal and it follows that approximate normal, has that bell curve, we can use what we call the empirical rule, which we'll learn about later, and that would mean that almost all of our data values fall within 3 standard deviations of the mean. So if I told you that we had a test that was approximately normally distributed and the standard deviation was 5, well, that means, so say our test was an average of 70 with a standard deviation of 5. As long as it had a bell curve, what that means is we could start at 70, 75, 80, 85. Well, this is a terrible test. This is a horrible test. This would not happen to us. But that would mean almost all the data on this test is between a 55 and an 85. That's what that within 3 standard deviations thing means. We can kind of do these bunny hops out from our mean in both directions to figure out what sort of our parameters are for normal. So we're starting to see how that standard deviation measurement might be used to sort of signify something's an outlier for pretty data. Just to sort of show this in action, I went ahead and simulated data. These particular distributions work from something that had a true mean of 0. And in this case, the standard deviation was 1. So you can see that 3 little bunny hop rule applies. 3 bunny hops out in both directions. Here, just to show you what spread does, I kept the mean at 0, but I changed that standard deviation to 2. So now if we took your bunny hops, they're just going to be a little wider because they'll be 2 instead of 1 wide. And almost all of our data falls within that. We do have one little guy who was a little bit crazy acting outside of that. There is one more measure of spread here, and that's the variance. The variance is literally just the standard deviation squared. So you just take whatever you get for that standard deviation and you square it. I don't particularly like working with variance because standard deviation has the same units, as whatever you're dealing with. So if you're talking about heights, you can say like the average height is, I have no idea, let's say we're talking about one like 64 inches. If you have a standard deviation, whatever it is also going to be in inches. So that's why I like standard deviation. It has the same units as our actual observations that we're talking about. Variance has units squared, which is very hard to interpret. It doesn't have this little 3 bunny hop rule. It's just a definition I put in here in case you take another stats class and you see the word variance. You know that means if I take the square root, it's back to the standard deviation, which is something we should feel more comfortable with. What does matter about variance, though, is that depending on what stats program you're working in, some will ask for standard deviation and some will ask for variance. So you have to pay close attention to what you're being asked for. Everything we do in this class uses standard deviation. For every measure of spread, we had these general properties. They are what we saw in that Rate My Professor example. As we get further and further apart, as the values get further apart, the measure of spread is bigger. And for all of them, they are all greater than or equal to 0. There is no way to have a negative spread. That doesn't exist. So you either have no spread, everything's exactly the same, or you have some spread. So I gave away a little bit on this, but I want you guys to take a moment, pause, and try out this true-false example. So true-false questions tend to be the ones students get wrong the most on my test. If I put true-false on there, like people get them wrong at a rate that is worse than if they had just randomly guessed. So first one here, if the standard deviation is 0, then all the data values must be the same. This is true. This is true. We just saw that example with Professor Lupin, I think was the one I had with the 3s. So there it is. If there's any deviation at all from the mean, there's going to be a value. It could be very, very small, but as soon as we have something to add up, then that numerator is going to exist. And when we take a square root, it's still going to exist. So they all have to be the same so that you can have 0 deviation from the mean. So the second one, if the IQR is 0, then all the data values are the same. This is false. Because remember, the IQR is just Q3 minus Q1. We have no idea what's going on in the upper 25 or lower 25%. We could have a data set that looks like this. Right? This would definitely have an IQR of 0 because the spread in that middle half of your data is nothing, 2 to 2. But outside of that middle, there's stuff going on. The last one here, if the range is 0, then all the data values must be the same. This is true. Your range is your max minus your min. If things are in order, the only way the max and the min are the same is if everything is the exact same, right? Think of this previous example. There's no way that you can write a little data set where that is not true. So I have the steps that we went over in the calculator for the 83 and 84 here, if you needed them. I haven't written up steps for the 36, but again, we will have a chance in class on Tuesday for you guys to try out the calculator stuff. Ugh, there's more. So, all right, I can fit this in a minute. The most important thing we've come away from is what to use when. That's the big piece here. And that is why this particular question has been on exams before. Is this idea of, look, here I've given you a display and I'm asking you about what measures we should use. So it's got both displays and measures. For the females, we're asked what type of center should we be using? Well, then the question is just, is the data pretty or ugly, right? Because we have this nice rule. We could almost make a little 2x2 table. The 2x2 table, if I made it, would say, we learned about measures of center. We learned about measures of spread. We learned that we have certain stuff that we should use when we have pretty symmetric data. And we learned that there are measures that we should use when our data is ugly because it has outliers or a skew, right? So for pretty data, which is what the females are, right? We need to decide, and don't get hung up. I had students who are like, but there's one more. It's freaking close to symmetric. What measure of center goes along with the pretty data? Well, that's the time that we are allowed to bring in all of the data, right? We are going to average everything. We're going to look at a mean. So that's our choice of center. And oops, I don't know why I'm trying to add a D to that. And our measure of spread that goes along with that is the one we just learned about, the standard deviation. Okay, and our justification, our data is symmetric. That's it. This is usually what I put on the test. I don't even have this calculation part because to me, this is the important piece. The calculator does the calculation part. For the male data, I come over to this side. Is this pretty? Hell no. This is not pretty at all, which means we need to be looking at our ugly data options. So what are our options for ugly data? For the center, this is when we want to use that median, the middle value. It ignores these couple of low scoring males from the bowling tournament. So there we go, median. And the measure of spread that goes along with that median is the IQR. So this table is something that's on every single exam. IQR. Something you might want to throw on that note card, right? More note card stuff. All right, and the justification here is that our data is skewed. And if you're telling me something's skewed, you should be telling me the direction. I want you to take a moment to decide, is that skewed to the left or skewed to the right? So this should have been skewed to the left. Students always get confused because they want to turn the screen, but if you turn the screen, not the screen, but the paper, what happens is your numbers are decreasing to the right, which doesn't make sense. So look at where this tail is. It's towards the lower values, which would be on the left on a number line. So this is skewed to the left. Calculating all of these is something you should do in your calculator, and I will go ahead and do that and then pop the answers in so you can also check. And these are the actual calculated values. The only one that I usually emphasize students actually checking to see if they can get on their own is this one for the female standard deviation, just to make sure that you're grabbing S off your calculator and not sigma, since they are truly both standard deviations. But remember, in this class, we're always going to be grabbing S because it's the sample standard deviation and you're doing statistics. So the last little blurb here is this idea of our 5-number summary. The 5-number summary is the min, Q1, median, Q3, and the max. And they want us to go ahead and do this for the male scores. Now, I already have some of this up above because I just calculated the median and the IQR for the male scores. So the median for the male scores was 278. I'm just going to go ahead and write it here. Q3 was 286. Q1 was 268. The minimum value for the males is a 240. And the maximum value for the males is a 289. And I realize now that some students may have been confused how I entered these values. Remember our stem and leaf plot, the 2, 4, and the 0 go back together. They sort of get like glued back together. So these are what your data values are for the men as I put them in my calculator. So that's it on spread. Whew. We got one big section left before Tuesday, and that's it.